Yeah. Okay. Yeah, I don't know what we can do about the microphone. I think people were complaining that the sound is not so good on the videos. I don't know what to do there. You have trouble understanding the sound on the video? No. Okay. Okay, so let's start. So Happy New Year, everyone. Today we are going to talk about rotation and isometries, basically, and we're going to introduce Lie groups. The idea is that, so we had a first lecture on differential equations, and we saw how to analytically solve differential equations, and we're going to use this a little bit today. And then we saw, just before the Christmas break, we saw the kind of manifolds, differential manifolds, and we saw some examples of that, like the sphere and so on. And so today we're going to take that material that we saw before the break, and we're going to add some axioms which are going to make these differential manifolds groups, and we're going to see where that applies. The main example of a Lie group is the matrix group. So that's the general linear group. Basically, all the squared matrices that are invertible together compose a group, and that group is the Lie group. It's also a differential manifold. And then we can see subgroups of that, and of course, so the special orthogonal group and the special Euclidean group, these are two differential manifolds that arise everywhere when in intelligent systems. So if you have, I will talk about that, but if you have an autonomous car, a robot, even if you're like predicting movement, all these kinds of applications make predictions or control parameters which have themselves a specific geometrical structure by themselves being a subgroup of this general linear group. Okay, so so rotations and isometries, they are basically the thing that arise when we are considering the geometry of the environment, like the world, the three-dimensional world, the Euclidean, the Cartesian space. And as soon as we are building some intelligent system that is going to act or perceive or reason or make some predictions about the Cartesian space, we are going to involve these rotations and isometries. So for example, if you have the pose of an object, if you're considering the velocity of rigid bodies, if you're considering the robot configuration space, so all these kind of perception, robotic tasks are going to involve rotations and isometries. And typically when we model the world kinematic, that's important for perception, control, and learning. And that's what we are talking about today. It's this kind of the fundamental mathematics of kinematics. We're not going to talk about kinematic chains. We're just going to lock down on what I said, so these subgroup of the general linear group, which are these rotation matrices or these affine matrices that are these rigid body motions, they are called, these affine matrices. We already saw them, but now we're going to look at them from a different angle. So we're going to introduce the exponential and logarithmic maps, which we didn't do last time. So last time almost no one was here. So I just suppose that you watched the video. We are going to rely on the content that I posted just before the break, so that you know. But in that content, we didn't go over some very key concept of Riemannian geometry, which are the exponential and logarithmic map. So we're first going to pause there and go over these two concepts. Then we're going to introduce Lie groups. As I said, it's just a differential manifold with a bunch of axioms, these axioms being the group axioms. And then we're going to talk about the rotation group in much more detail, Especially, we're going to look at the structure of the exponential map of the rotation group, and that is the Euler-Rodriguez formula. So as usual, if we have our autonomous vehicle, then quaternions here might define the kind of configuration of the pedestrians, or we might predict in that space, like for example, like these are like 3D rotations. Angular velocities are going to be the space of pure quaternions for the quaternion. So if you have a three-dimensional rotation, which is described as a quaternion, then its angular velocity is going to be a pure quaternion. I will talk about this a little bit more, maybe at the end. Then rigid motions, which is the mathematical formalization of isometries, they can be formalized as a matrix, which is or a family of matrices, a group of matrices, which is a subgroup of the general linear group, which is called the special Euclidean group. We talked about this. You should remember that the structure, it has an orthogonal matrix on the top corner. Well, on the top corner here, then it has a zero line and then a 1, and the translation is a column vector on the right side of the matrix. It's an affine matrix where the affine part is an orthogonal, it's a special orthogonal matrix, meaning with determinant 1. And so the velocities of these rigid body motions are special matrices that belong to something that we are going to introduce, which is called the Lie algebra, which is simply the tangent space at the origin of the group. Okay, so that's our outline today. We are first going to talk about, introduce these exponential and logarithmic maps, and then the Lie groups, and then the kind of exponential map of the rotation group. So, coming back to Riemannian geometry, what is the exponential map and what is the logarithmic map? And before we do that, we can just give a little bit of context of where do manifolds arise in practice, also, for example, in robotics. So here are the two canonical examples that we are going to talk about in this section. So we have on the left side, this is the space of quaternions. So quaternions are four-dimensional vectors, and they live on the surface of a hypersphere of dimension 3. Sorry. So the surface of the sphere is of dimension 3, and then the embedding space is of dimension 4. So meaning that if you have two quaternions and you want to compute the shortest way of moving, so quaternion actually represents the orientation of a rigid body. So if I have a rigid body, that a quaternion will fully specify how oriented it is in three-dimensional space. And then I have maybe another quaternion here. The question you might be asking is, what is the kind of shortest movement that brings me from one orientation to the other orientation? And that is going to be, at least in this definition, you can define different metrics which are going to serve as, so different Riemannian metrics, which are going to serve as a way to compute the shortest path. But in the case of quaternion, the embedding through the induced metric prescribes shortest paths, which are these big arcs on the three-dimensional surface sphere. Okay, so this is what's depicted here. So you have, let's say, that's a quaternion, and then the shortest path to that quaternion is going to be this great arc here. Okay, so that's for that. So in robotics, you might have some constraint on the orientation of the end effector, and you want to introduce that in some optimal control algorithm, or maybe some learning algorithm, maybe some reinforcement learning algorithm. Then you need to have a proper way to interpolate between two orientation of the end effector And this would prescribe a way to interpolate correctly on that. So here we have the group of semi-positive definite matrices. So I put, positive definite matrices. So it's a squared matrix here. And positive definite means that if you take the inner product with respect to that metric here, to that matrix, then it will always be positive. So yeah, so the hypersphere of dimension 3 is the set of vectors of dimension 4, which dot product is 1. And yeah, it's the manifold, it's isomorphic to the manifold of unit quaternions, and can be used to represent 3D orientation, like something like the robot ion effector. And then this other group, which is depicted on the right side here, is going to be the space or the set of squared matrices. So here I took the example of dimension 6. And this is a manifold as well of symmetric positive definite matrices. It can be used in robotics, for example, to represent the manipulability ellipsoids, meaning what is the manipulation capability of a manipulator, so like a kinematic chain. So that manipulator here composes a kinematic chain through the product of its joints, and then the semi-positive definite matrix is going to tell you how much velocities can you generate in the end effector space for a given configuration. So you can imagine if you are extended, then you cannot generate any velocity going toward if your base is fixed, but you can generate velocity in that direction, or especially you can generate tangential velocities, but not so much like in this direction. So that differential thing is that explains that is the manipulability ellipsoid. So yeah, it's the set of square matrices which are equal to their transpose, meaning that they are symmetric, and then they are positive definite, and that's the definition here. Okay, so these are two manifolds. They are not subgroups of the general linear group, though I'm not 100% sure for this one, but definitely this one not. So the question is, so how do we compute geodesics between those? So let's take the example of the sphere of dimension d, where d is the dimension of the surface of the sphere. So if we have S2, this is the classical globe sphere. Then the geodesics here have this, we all know this, it's this intuitive thing that if you want to take the shortest path between 2 points on the surface of the globe, you're going to follow these great arcs. So here we have these 2 points, and the geodesics between P and Q is the red line. But so coming back to before the break, so a geodesic is a minimizer of the energy function, and the energy function relies or includes the metric tensor, okay, the Riemannian metric tensor. So we do have a closed form for the geodesic distance between P and Q, and if you're just considering this spherical manifold, so the hypersphere of radius 1, where it's the collection of points which have a 1 dot product. So their distance to the origin is 1, right? The length here is going to be simply the arc cos of the dot product between the coordinates, and that's it. If you had if you had like a radius which was not 1, then you would have the radius that would appear there. So to remind what is the Riemannian metric that we use here, or that we imply here, it is the pullback metric through the embedding in RD plus 1, where again, D for the globe would be 2, and D plus 1 is the embedding space, so it's the three-dimensional space. It is also called the induced metric. Okay, so it's simply that we are measuring distances with respect to the Euclidean distance in three-dimensional space, but we are constraining ourselves to remain on the surface of the globe, and so the geodesic is simply going to curve around minimally between the point, kind of like follow follow the minimizer of that. And for the sphere, yeah, we have a nice closed form solution for the distance. So for the case of the semi-positive definite matrices, they form a cone, and you can see it like this. So, so this is the manifold of semi-positive matrices of 2 by 2, so these little squares, and the valid specification of these matrices is going to be when Z is positive. So Z is one of the coefficient of the matrix, and they have this. Remember that they are symmetric, right? So they are symmetric with respect to the main diagonal. So you can find X and X here and there, and then Y, and yeah, and this other constraint here that has to do with the semi-positiveness or positiveness. It makes it so that matrices have to be within this cone. So any point in three-dimensional space is going to specify a matrix through these coordinates here. Now, this, if we used the induced metric using this three-dimensional space, of course, the straight line would simply be, so the geodesic would simply be a straight line. But this doesn't provide a good metric for semi-positive definite matrices, and usually the metric that's used for these matrices is the following here that I put here. And it basically comes from when you're considering a log barrier, so you're trying to avoid the boundaries of what is possible to do in terms of this cone. You basically end up with geodesics that curve like that, okay? Yeah. So they are embedded in the manifold of symmetric matrices SIM2, which is also actually the tangent space of this manifold. And given that Riemannian metric that I just explained that arises from the log barrier, the length of geodesics also have a closed form solution, and this is what it is. One thing to note with Riemannian metrics is that they provide a coordinate invariance for the geodesics. Meaning, if we are just considering the simple example of the two-dimensional plane, Euclidean plane, and we have two ways of specifying vectors. We can specify vectors through polar coordinates, or we can specify vectors through Euclidean coordinates. We define the geodesics as being straight lines with respect to the Euclidean metric. And the idea is that if we have this notion of geodesic, we would want that it does not depend on the way that we are choosing our system of coordinates for the vectors. And the way we do that is by basically changing the Riemannian metric, so including in the Riemannian metric the change of coordinates. So the way this is done for the simple example is we have that the Euclidean distance, we express it in terms of the coordinate, and also this is the infinitesimal Euclidean distance. And with respect to this other system, coordinate system, which is the polar coordinate system, we solve and we get this. And we can express this as a matrix multiplying the vector of coordinates, here the polar coordinates. And what we get is this metric tensor, which is then the same metric, so meaning this is the Euclidean distance, but instead of being the identity, it is function of the radius. So how far? So how far you are from the origin? R. Okay. Yeah. So we can, if we define geodesics to behave in a particular way, then the metric tensor, the Riemannian metric tensor, will include the change of coordinates if we change coordinates, and the geodesics will not change themselves. Okay, so one last thing is to introduce these exponential and logarithmic maps. And it's the basic idea of how do we go from the tangent space to the manifold itself. The key idea is that a Riemannian manifold is in general not a vector space, since it is not closed under addition. So if you're on the surface of the sphere and you add two vectors together, or 2 points from that manifold, you will end up outside of the manifold. That's the key idea. So you cannot do algebraic operation on the manifold. But you can do that on the tangent space. So we saw last time that the tangent space is a vector space. So how can we, so we would want to do a lot of the calculation in the tangent space. So how can we go back and forth between the tangent space and the manifold? So let's take the simple example of the circle, which is the sphere 1, okay? So we can parameterize the circle using complex numbers. So we have the real axis and the imaginary axis, and this is Euler's formula, meaning that it's using the exponential of a pure imaginary number and relates that to the coordinates on the complex plane. What we have here can be seen as the tangent space at 1. 1 is the complex number that only has a real part. That's 1 and doesn't have any imaginary part. So we're here on the complex plane, and we draw a line. This is the imaginary line. It's parallel to this one. I mean, it's the same thing here. And so this is the tangent space to that point here. So that's the unit circle, or the sphere 1, and we parameterize it with complex numbers, and it's defined as the inverse of the z times z is equal to 1. The inverse, I put it here, so the inverse of a complex number is the conjugate, and the conjugate is defined here. The idea of this conjugation is that if you have a rotation, you can do the inverse of that rotation, and if you then add them together, you get like the zero kind of rotation. That operation makes the circle actually is a group, but we'll come back to that later. Okay, so if we differentiate the constraint, the manifold constraint here, we get 0 on the right side because we are differentiating 1 with respect to time. So 1 with respect to time 0. It's a constant. And then we have the product rule that applies. So we have A times B, and we differentiate that with respect to time. And this would be A dot B plus A B dot. So this is what is written here. And this is equal to to a complex, this is actually a pure imaginary number, and it's equal to this, to this set here. So if we rearrange that equation here, that equation here, we get that equation, which is an ODE. We saw that in 2 weeks ago, or two lectures ago. And we can solve that first order ODE, and we get that z of t is equal to z0 times the exponential of tau times the t. Okay? Yeah. How did the differentiation happen? So what we are doing here is saying that z is a function of time. So you have 0, it's here, and then z specifies the entire curve, like potential points like along the circle. And then we differentiate that with respect to time. And yeah, so we.
I don't get the -1. What is like minus z, the power of -1?
So you mean here?
No, down.
Here?
Yes, not minus.
So yeah, I went maybe a little bit too quick. But I explained. So here we have two factors. You could say this is the first factor and then the second factor. And then we just apply the product rule of differentiation. So if you have the product rule, if you have A times B, they're both function of time, and you differentiate that with respect to time, you will get A dot B plus A B dot. And then if you rearrange, if you pass like one of the terms on the other side of the equation, because it's equal to 0 here, then you get that. And then the key idea, is that you reason at the identity. So basically, you're saying that at the identity z is equal to 1. No. Okay, I will write it down. So this is, by the way, this is the simple example, but we'll come back to that for the rotations and so on. So it's always, because this, as I said, this is a group, so it's a Lie group. We haven't introduced the Lie group yet, but so this key idea that you differentiate the group constraint and then you come up with the tangent space at the identity. This is super core to Lie groups. So we're going to see that like 2 or 3 times. But the idea is that you have z minus 1 z is equal to z minus 1 z dot. And then you say, let's consider the identity. So where z is equal to 1, the points are there. Then what you get is z minus 1 is equal to minus z. You understood how we got this equation, right?
No, now I got it. But the next step, like when we got the relation z dot equal to z tau.
Yeah, so I'll do that. So then you have z is equal to 1, so this is just cancelled, and you get z dot minus 1 is equal to minus z inverse times z dot. And then maybe the best way, No, maybe, so you have to only like consider one of these at one. I would say maybe this is better. If this is 1, okay, it's equal to 1. Then you get z dot minus 1 times z is equal to z dot. And then you say, no. Sorry. This is equal to... This is equal to 1. I think I think the best is to identify that to tau, and then that to 1. And then you get your equation, which is tau is equal to minus or that to 1. Something like that. So yeah, I mean, the sign doesn't really matter here because I mean you can integrate it through tau, and then you get your differential equation here. Okay? It's a little bit, I don't know, hand wavy, the thing here. But the idea is that tau is, you associate tau with the tangent space, so it's the derivative of the curve. And it's the derivative of the curve at the identity, in this case at the identity. And then you're trying to, and then you're characterizing what would be then if you have a velocity tau at the origin, where would you end up on the circle? And it's linked to the exponential. And this is actually just Euler's formula in the case of the circle. Right? So if you have a velocity and you integrate that velocity and you remain on the circle, you will simply, depending on that velocity, end up, wherever, how the stronger that velocity, the more angle you will follow. And that velocity is constant, by the way. So that velocity, that initial velocity, or that velocity at the identity is a pure imaginary number. I think that's the key idea here to remember. Okay. So that's the exponential map in the case of the circle. It's just the exponential. And it comes from the ODE that arise from this from the group from the constraint here, from the constraint of being on the circle. Okay, so but generally, if we have a manifold that doesn't have necessarily this circle structure, we just use that. We borrow that name, this exponential map, and also the logarithmic map, to map back and forth from the tangent space to the manifold itself. So the manifold here is the gray sphere, and the tangent space is this green kind of plane, and the exponential and the logarithmic map are just names for mapping from the tangent space to the manifold using a geodesic. So it's if you're at point X on the manifold and you have an initial tangent vector u, where if you're following a geodesic in the direction of u, would you land on the manifold? And that's y. So point x and y are on the manifold, and the vector u is a vector from the vector space Txm, so the vector space that is attached to the point x on the manifold. And yeah, so again, so the exponential map associates a vector u in the tangent space at x to a point y, which is reached by the geodesic at time 1. And so the distance between x and y is actually u at x. Okay, so the generic structure of the exponential map I just explained, but this is a more, so this is like the true exponential map, the one that uses actually time, because the exponential map is a function of time, so it specifies the geodesic, like how all the points along the geodesic. So if you have a tangent space that is attached at point P0, and you're considering the exponential, map at that point in the direction of some tangent vector here called theta, you will have, you will specify, it will be a map that will map these vectors to all the points that are along that geodesic here. And then the logarithmic map is the inverse map, so it's also defined for point P0. It's attached at a certain tangent plane or space, and it will take a point from the manifold and pull it back to the tangent space, and then tell you what is this vector here, theta. So it maps points on the manifold to vectors on the tangent space. Okay? So that's just the generic concept of the exponential and the logarithmic map for Riemannian manifolds. And it's a function of the Riemannian metric that you're using on the manifold. So there are closed form solutions for the two examples that I mentioned in robotics. So for the hypersphere, you will have the exponential map is expressed like that. So it's the exponential is the sum of the cosine and the sine of the x vector here and the u vector. That's the structure of the logarithmic map for the hypersphere. And for the space of symmetric positive definite matrices, we have the exponential map, which is linked to the matrix exponential, and the logarithmic map, which is linked to the logarithmic, the matrix logarithm. Okay, so I don't explain how we derive these quantities. We will come back actually to this. Okay, so that was it. Now we're gonna talk a little bit about Lie group if we do have time. Okay. Do you have any questions? No. Okay. So yeah, in the general case, if you have a general manifold, we do not have to have a closed form solution for the exponential and logarithmic maps. And sometimes we approximate these maps. But if, it's the key idea of understanding the notion that there's a tangent space and so on, is that if you design perception, learning, and control algorithms, you need to be careful to not, for instance, add vectors from a manifold and then land outside of the manifold. You have to reason then on this idea of the tangent space and then mapping the things back to the manifold using the exponential map. There's also a concept that I did not introduce, which is the parallel transport, things like that. So if you are doing computation on a manifold, you might want to integrate in your algorithms these kind of closed form solutions at some point. Okay, so the Lie groups. The definition of the Lie group, as I said in the beginning, it's simply same. It's a smooth manifold, and actually we already saw two Lie groups. So S1 is a Lie group, S2 is not a Lie group, S3 is a Lie group, and that's it. That's all the Lie groups that we saw. It's a smooth manifold, meaning that it's a topological space that is locally homeomorphic to Euclidean space. So topological space means that it has a neighborhood structure, and then locally homeomorphic means kind of looks like Euclidean space. Locally homeomorphic, we saw what it means last week. You can kind of get to this notion using these charts and so on. So it's basically you have some kind of like continuous mapping between the surface of the manifold and Euclidean space. And the elements of this manifold satisfy the axioms of a group. And when that's the case, then you have a Lie group. So that's it for what a Lie group is, basically. So let's go back to the axioms of a group. So we have closure under the composition operation. So a group is simply a set and an operation between the elements of that group. That operation between two elements of that group makes another element of the group. And closure means that that operation always generates members or elements that are going to be in the set that we are considering. So that it's closed under that operation. It has a neutral element. We talked about this in the early lecture. The neutral element means that if you compose one element from that set with the neutral element, it's going to spit out the same element. It has an inverse element, and that's where we use the neutral element to introduce that, meaning that every single member of the group can be composed with its inverse that generates the neutral element. So it's saying, so X, let's say, plus or times the inverse is equal to the neutral element. So in the case of multiplication, this would be the reciprocal. So A times the inverse of A is equal to 1. In the case of addition, this would be a minus, so the opposite. So if you have, let's say, 5 minus or plus minus 5, then you get 0. So associativity, yeah, so that's clear. So the key example of a Lie group, as I said that in the beginning, is the general linear group. They are of dimension n, so of the reals. What it means is that it's all the squared matrices that have a determinant that doesn't vanish. So all these matrices are invertible, and the composition operation there of that group is matrix multiplication, also known as the group of invertible matrices, non-singular matrices. And the neutral element is simply the identity matrix. So it's a matrix full of zeros, and on the diagonal you have ones. That's the identity matrix. This n here means that it's a squared matrix with this diagonal elements. So key facts about the Lie group manifold. So as I said, the unit circle is a Lie group, and the exponential map, what it does is that it maps the tangent space at the origin, which is this guy, the line, the pure imaginary line, to the distance that you would go on the circle to reach, so what would be the particular point if you applied that, the tangent element here? So the key thing to consider here is that the tangent space at the origin here, so one, the complex number that has only a real part 1 is the neutral element of S1, which is a Lie group. And so you could say, so this is the tangent space at the origin. It's isomorphic to the real line. So isomorphic for vector spaces or generally means that if V is isomorphic to W, so that symbol just means that V is isomorphic to W. And the key fact that we saw in linear algebra is that all vector spaces, all of them, are isomorphic to Rn, where n is the dimension of the vector space, and the dimension of a vector space is the minimal number of generating basis vectors that you need to express all the vectors in your vector space. Remember that a vector space is also a group. So yeah, that thing here is called the Lie algebra. Yeah. So composition of elements remain on the manifold. That's like a very key fact. So we introduced that composition operation for the group. So we have the set. Let's say so on the manifold we kind of only had the set. We didn't have a notion that we could compose elements from the set. Now on the Lie group we have the composition between elements that generates another element from the manifold. And composition between two elements of the manifold will generate another element on the manifold. That's the key fact. Each element has an inverse on the manifold. The manifold looks the same at every point, and that's advanced. I mean, it's not obvious, but just to get a feel, just look at the unit circle. If you look locally on the unit circle, everything looks the same, right? And there's a special element called the identity. And as I said, for the unit circle, this is z is equal to 1. So it's a complex number where it's this point here. And the tangent space at that point is called the Lie algebra. So that's a key point. The Lie algebra is a vector space, but it's also an algebra. But algebra is just another, you put on another axiom on top of the vector space in this case. Actually, it's usually on top of groups, I think. But we don't, and as I said, a vector space is already a group. We don't really care about the notion that it's an algebra in this lecture. It has to do with the Lie bracket operation, which we won't introduce. But we're going to focus on the tangent space. So the Lie group M, which is also a manifold, has a tangent space at the origin, just like at every point on the manifold. But this one is a little bit particular for the identity element, for the neutral element. And we call that tangent space the Lie algebra. Just like all the other tangent spaces, it has a vector space structure. And we define these kinds of symbols for the Lie algebra. Lie algebras are very important because of that third fact, which is that Lie groups are very similar or almost the same point to point. Like the tangent spaces are very similar. So we can always reason at the origin and simplifies a lot of things. So just like any other vector space, the Lie algebra is isomorphic to Rn, where n is the dimension of the Lie algebra. The exponential map in the case of Lie groups is so in the case of Lie groups, usually you define two types of exponential maps. Maybe it's the same in Riemann geometry, I'm not so sure. The lower capital exponential and the capital exponential. The lower one takes elements of the Lie algebra, and the capital one takes elements of the isomorphic Rn. So it's kind of like the coordinate vector elements. So how do we characterize the Lie algebra for a Lie group? And we come back to that equation here that I drew on the board. That's key. It's by differentiating the inverse element group axiom. So remember, Lie groups are manifolds, but on top of that, they have another bunch of constraints associated to them. And one of them is that there's an inverse element to each of the elements of the group, and this is equal to the identity. Now, if we time differentiate that constraint, and we apply the product rule, we get that. And then by rearranging the terms, we get that. And by considering things at the identity, which is what I try to do here, but I'm not sure I get it completely right. I think it's you set basically this one to one, and then you get that this one you kind of factor the sign in the other, and that it's an inverse also doesn't matter. You're just like kind of like considering the flip. And so that basically says x dot, or like things that behave like velocities are equal to x minus 1 times x dot, and then you get your ODE equation. So that's the characterization of the Lie algebra elements. So the basic kind of reasoning here. Okay, let's take the example of the Lie algebra of the rotation group. So the rotation group, there are two rotation groups, of interest. So there's the one on the plane and the one in 3 dimension. When I say rotation group, I'm talking about the one in 3D. So it's these orthogonal matrices of dimension 3. So orthogonal matrix means that we have R transpose times R is equal to the identity. And also that, so here it's the special group, so that the determinant is equal to 1. This is a subgroup of the general linear group. And so the orthogonality condition is the group axiom, because for these matrices, the inverse of the matrix is equal to the transpose of the matrix. That's just like the constraint that we have on that subgroup. So the orthogonality condition is actually also the group axiom in that case. And we can derive that group axiom or that orthogonality condition, and we arrive here, which is the characterization of our Lie algebra elements of the tangent space at the origin. And these are all skew symmetric matrices. What does it mean? So skew symmetric simply means that the negative of the matrix, so that the matrix itself is equal to the negative of its transpose. And that's what this expresses here. So here, if we transpose that, we get this, and then we take the negative, and it's this, and we say that this is equal to the negative of its transpose. And the only matrices that are equal to the negative of their transpose are the skew symmetric matrices. And actually they have a weird form, which is this form here in 3 dimension. So you can construct them they only have 3 degrees of freedom. They don't have a trace, so the diagonal is all zeros traceless matrices. And they, so you can construct them like that. So that's a symbol that's used in math a lot. It's saying you take a vector, and you, that vector being omega here, which has 3 components, and you construct the skew-symmetric matrix based on the components of that vector, and that gives you this matrix here. Okay, so I mean, that's one view. So we have the constraint, the group constraint for these matrices. We time differentiate the group constraint, and we identify that the matrices that obey that group constraint have to be skew-symmetric matrices. Okay? Those are the elements of the tangent space at the identity, the Lie algebra. So now we could ask ourselves, can we come up with a basis for the Lie algebra? And we can. So if you look at the structure of the skew-symmetric matrices, there's one number here, another number here, and another number here. So by having 3 matrices which multiply these scalars, this 3-dimensional vector, these are the 3 matrices, we can come up with this basis for the Lie algebra. And a basis is a linear combination of matrices that compose the skew-symmetric matrices. So that's what that is. And now we have fully defined our Lie algebra, the tangent space at the origin. Origin meaning the neutral element or the identity element. Here it's the identity matrix. So we have that our Lie algebra is isomorphic to R3. And remember, so when a vector space is isomorphic to Rn, n is the dimension of that vector space. So that vector space, so the Lie algebra of SO3 has dimension 3 as well. Okay, so another thing to introduce is before we finish with the Lie groups, is the group axiom, the group actions, and that means that it's a thing that it's a map that takes the Lie group and takes some vector or set and outputs some element of the set, and it's called an action of an element of the Lie group on the set element if the action of the identity element spits out the same element, and there's this kind of compatibility structure here. So these are examples of classic actions on these classic groups. I guess the most interesting one is the one of SEN, which is if you use an element of the special Euclidean group and you compose it with a vector, you will get the vector offset by that transform here. So rotated and translated. I wanted to talk about the joint map, but I think I'm running out of time. So the key idea of the adjoint map, this is advanced but also very interesting, is that if you are mapping from point X, from the identity to some point Y, and you do it through some Lie element X, and then some element delta, then the element delta will have different coordinates if you're going through a different path, even though it's the same X here. If you start by the delta and then you add X, this will have a different path. But these paths are specified by the exponential map of some tangent space vectors, and they are connected to each other by a linear map. And that has to do with the properties of the exponential map. And that linear map is called the adjoint map. And of course, because it's a linear map, it has a matrix coordinate, which is this ADX. And here is an example of there are closed form solution for this adjoint map. And this adjoint, so here is the coordinates version, also so the closed form solution of that matrix for the spatial Euclidean group of dimension 3. So what you do is you simply initially express it like that. So this introduces the V map, which maps elements of the Lie algebra to the isomorphic Euclidean space, or Euclidean vector space. And then you eventually get the adjoint closed form solution matrix here. But yeah, I don't have time. I want to focus more on what comes. So all of what we talked about in terms of the Lie algebra structures for the circle, the 2D rotation, the rigid motions in 2D, and then in 3D, the sphere, the rotation, and the rigid motions in 3D are summarized here. There you have the group constraint, and you have the dimensions of the manifolds, and you have the exponential maps, which is basically always some kind of exponential here. Because this has to do with solving the ODE of differentiating the constraint. It's not exactly it's very, very related to the exponential map of Riemannian geometry. Sometimes it coincides, but it doesn't have to be, because the Riemannian geometry exponential map relies on the Riemannian metric, and here we haven't really talked about Riemannian metrics. Okay, so I wanted to talk about the Euler-Rodriguez formula and the rotation group in more detail. So what is the Euler-Rodriguez formula? Did any of you hear about this before? No. So the Euler-Rodriguez formula is a thing that rotates a vector v around an axis k by an angle theta. So the axis of rotation is k. The vector that's being rotated is v. And the result is v rotated. So basically, if you have k and you have some vector v, the idea is I give you a theta and I give you this k. How would I end up rotating that vector with respect to k? Okay, by an angle theta. So k, v, and then and I get v rotated. That's the basic idea. So the formula characterizes the rotation of vector v, and you can decompose v between its parallel component, v parallel, and then its orthogonal component with respect to k, which is going to be v orthogonal, v bottom. So that's okay. Around the axis k, and then by an angle theta, there. It can be used to rotate basis vectors of a frame from an axis angle representation. Remember, maybe I don't know if I said this before, but 3D rotations can be represented by 3D rotation orthogonal matrices. This is what we just saw, but also by axis angle. And that means that you have unit axis, and then you have an angle around that axis, and you can factor the angle as the norm of the vector. So you basically, if you want to recover the angle, you just normalize that vector, and the factor by which you normalize it will be theta. So it expresses the fact that rotations in 3 dimensions have only 3 degrees of freedom, because rotation matrices, without the constraint, considering the constraint, orthogonal matrices have 9 numbers, but they only have 3 degrees of freedom that arise from the orthogonality constraint. Okay, so because you can use this kind of scheme to rotate basis vectors of a frame from an axis angle representation, it provides a way to change the representation of a matrix from an axis angle of 3D rotation from an axis angle representation to a rotation matrix, an orthogonal rotation matrix. Meaning that it provides a solution for the exponential map of the special orthogonal group. So mapping elements from the Lie algebra to elements of the manifold in closed form. So the key idea is, how can we express the vector vrot, so v rotation, this one, the blue one, as a function of the red one, k, and the angle theta. And that will be the Euler-Rodriguez formula. Okay, so basic derivation of the formula. We first express that V can be decomposed as the parallel with respect to K and the orthogonal part with respect to K. Then we express that the orthogonal part of V rotation, which is this part here, is the combination, so the coordinates on the orthogonal plane. Okay, so it's going to be the cosine times this of theta, and then the sine of theta times the orthogonal vector. It's just the coordinate of that vector on the orthogonal plane. Okay? And then V parallel, we can simply express it. Remember from the geometry lecture, this operator is simply the orthogonal projector of a vector. So if I multiply K transpose by V, so K transpose has to do with this vector by V, I will just get the orthogonal projection on that line here. So it will be V parallel. Then I have that V parallel, so V orthogonal here is equal to V minus V parallel, of course. So that's just saying V is equal to V orthogonal plus V parallel. Then I just switch it. Then I use that definition again, that V parallel is just the projection onto K of V, and I use the projection operator, which is the outer product of K. And finally, I use the definition that the W vector, which we took for granted, is the cross product between K and V. All right. Now I can substitute 3 and 4 into 2. So I use these 2 equations that I posed, and I then substitute them in there. So what happens is that I have the V, this guy is this guy, so it ended up here. And then I have W, that was the cross product here, replaces W here. And then I just rearrange the terms because I have this thing that appears twice. So it appears here, and then that's pretty much it. This is the Rodriguez formula. That's it. So what we have is the rotation of a vector v, the red one, with respect to an axis k by an angle theta, and we express this vector purely with respect to these components. So theta, the initial vector, and then the vector k, and that's it. We have a formula that links these three things together in order to generate the coordinates of vector v rotated, the blue one. All right. So the next step is to put that into a matrix equation. And the way we do that is we factor by v. And in order to factor by v, we have to introduce an identity matrix here, and we have to introduce a skew-symmetric matrix. So the skew-symmetric matrix is the matrix such that, or the types of matrix such that, if we multiply a vector by a skewed symmetric matrix, we basically get the cross product between the vector that composes remember the skewed symmetric matrix only has 3 degrees of freedom, so it's a 3 vector, and if we multiply a vector by the skewed symmetric matrix, we get the cross product between that vector and the one that composes the skewed symmetric matrix. So this is the skewed symmetric matrix here. And this gives us the standard form of the Rodriguez formula. So now we have that if we have a vector and a rotation, which is an axis angle representation, we get an element of SO3, the special orthogonal group. So we have a way of converting an axis angle representation to an element of SO3. Okay? Just a slight detour on infinitesimal rotations. Let's consider the small rotations d theta. And in such cases, the sinusoid, the sinus of d theta is going to be d theta, because we're considering very small rotations, and a sine at the origin is basically the identity, right? And then cosine at the origin is basically flat, so it's basically 0. So if we plug that into the Rodriguez formula that we just saw, actually the one that rotates the vector, we have that is equal to d theta, and then we have that is equal to 0 because, that is equal to 1, sorry. That's a typo here. So cosinus theta, because it's flat, it's going to map to 1, not, so, right, it's not, well, it's flat and it's 1, right? So, that's sine, and then cosine is considering that, right? So that, so if we are here, sinus d theta is going to be d theta, and then cosine d theta is going to be 1. So 1 minus 1 is going to be 0, and so the higher order skewed term vanishes here. So we have that basically the differential of a of the rotation. That's also a typo. Well, I have to fix that slide. So of the rotation here is equal to the skewed symmetric matrix times the vector that we're rotating. Just to have in mind that the skewed symmetric matrix, yeah.
In the previous slide, I didn't get where went cos theta.
That what?
In the form of Rodriguez formula. Before the identity, I think, there was no cosine theta. On top.
This?
This one.
Yeah, you're right. I also have to check that out. Yeah, I remember seeing this, and I thought I addressed this. Yeah, I will check that out. I'll fix the slide here as well. Okay. Okay, so to finish, the rotation group is like that, and how can we derive the exponential map? Same thing, we take the time derivative of the orthogonal constraint, orthogonal condition, and remember that we get this ODE here. And so if we take R to be the identity, and we're then considering the tangent space at the identity, well, so if we don't consider the tangent space at the identity, just generally, we can solve that ODE using just the exponential. If you don't remember the derivation to go from there to there, 2 lectures ago we did the derivation. It's very simple. So because it's a separable differential equation, and so you just take the log and blah, 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 and then just 3 lines of derivation. Then, so if we do consider it at the identity, then R0 is the identity, and we can pose that omega t is equal to some vector R3, okay, in R3 with k a unit vector, and consider the origin. Then the exponential decomposes as a power series. So just the definition of the exponential. It has a power series decomposition. Using these elements of the Lie algebra. So by having n, so this is a matrix power, right? So it's multiplication by itself. So it writes down this way. And then if we consider that if we multiply skewed symmetric matrices, they actually alternate. So it's not that a to the power 4, 5, 6, 7, and so on generate new matrices. It's just there's a kind of alternating pattern. So basically, 0, we have the identity. 1, we have the skewed symmetric matrix itself. 2, the squared of a skewed symmetric matrix has this form. And then 3, it's already alternating, so we get 1, the negative of 1, and so on, so forth. Meaning that we can rearrange the terms as only using a, k, and a squared. So we get that the rotation matrix is like that. And we identify just using basic Taylor expansion of sine and cosine, that this is the sine of theta, and this is the cosine of theta, or 1 minus the cosine of theta, sorry. And so this is, again, the Rodriguez formula. So this is the key connection between the exponential map for SO3 and the Rodriguez formula. It's that you get it through this power series, and especially by identifying these Q-symmetric matrices. So, okay, final slide. We're late. So the group of unit quaternions. As I said in the beginning, unit quaternions are a way to represent 3D rotations. So generally, the quaternions are just the extension of the complex numbers to the three-dimensional case. It has a real part, and it has an imaginary part, and that imaginary part, instead of having one dimension, has 3 dimensions. And then there's like algebraic structure to combine these imaginary parts, which I won't get into just in this one slide. I just want to talk about the exponential map of the quaternion group. So it has a group structure, and because it has a group structure, we can do the same. It's also a manifold, it's also a group, it's a Lie group. We can do the same thing, differentiating the group constraint and identifying the Lie algebra. The Lie algebra is only the pure quaternion, meaning the quaternions that have 0 for the real part, so for this part here. And that's how you write the pure quaternion space or groups. And the vectors, and so there's an action that rotates vectors, where vectors are defined as pure quaternions. And this action is written like this. This is actually called the composition of quaternion numbers. And if you derive, it takes a bunch of pages to actually derive this, so I didn't put it on the slides. But this operation actually operates the Rodriguez formula as well. So it rotates the vector. And the exponential map of this Lie group writes down this way. And if you remember, this is the exponential map of the sphere 3. So the hypersphere, where the surface has 3 dimensions. And we can actually identify the following, that the real part is cosine theta over 2, and that the imaginary part, this pure quaternion part, is actually an axis angle representation, where instead of having the theta multiplying the unit vector, what it does is sine theta over 2. The key fact about these quaternions, at least in the context of manifolds, is that when we use quaternions, the exponential map corresponds to the induced Riemannian metric on S3. So it's not clear what was the Riemannian metric associated with the exponential map of the SO3 group. I mean, there's one associated to it. It has to do with something called the Killing form associated to the Lie algebra. But in the case of the hypersphere, it's the induced metric on S3, so just the classical thing that you would expect from the sphere, right? From the Euclidean metric that is induced on S3. Okay? So yeah, so the geodesics will, the ones that you get through the exponential map would then be these great arcs on the sphere, but of the sphere where the surface has a 3 dimension, not 2. So in summary, the exponential map allows to design algorithms that account or exploit the geometry of the parameter space. By encoding the geometry in the metric tensor, we do not rely on the choice of parameterization for the manifold. And Lie groups are smooth manifold, key fact, with a group structure. A common family of examples are the matrix groups, and we saw mainly 2 subgroups of the matrix group, the general linear group, the special orthogonal group, and the special Euclidean group. And a lot could be said about rotations, as I said, especially concerning metrics for rotations. like real proper distances for rotations. It's, well, whatever. We could say, I also didn't talk about like how is SO3 isomorphic to the group of quaternions. A lot could be said about that. A lot could be said about quaternions. I mean, I think if you want to pack everything into one lecture, we are limited to what we saw today. So to finish with differential geometry, because next week we are going to talk about probabilities, and we're going to switch gears, and then at the end we'll see optimization and then some examples, and then the semester will be over. So differential geometry considerations are fundamental to many applications, and more. So this is a theme of research that is still very active, and there's more and more realization, even though that started already in the 80s or even before in intelligent systems, that differential geometry was a base, very important base. Then it got somewhat lost, I would say, for 10 or 15 years, but it's coming back. So in state estimation, motion planning control, imitation learning and reinforcement learning and all that stuff from intelligent systems, differential geometry is key. If you look at recent paper from Yann Lequin, they have considerations of what kind of manifolds are used in deep neural networks. So they use differential geometry insights to think about what are deep neural networks actually doing, because the parameters of the neural network are actually a manifold, and reasoning in terms of differential geometry then makes a lot of sense. So yeah, I would say take time to understand differential geometry. It's a cool thing. Okay, so that's it. Do you have any questions?